So in this lesson, we're going to switch over from measurement to geometry, and we're going to look at the properties of angles in different shapes, including parallel lines like we see here. And there are certain properties that angles follow that allow us to find unknown angles in certain cases, as long as we have other pieces of information. So here we are with parallel lines, as we said. And with parallel lines, you will have learned in previous years of math that we have two different patterns. Whenever we have a line, or if you want to get really mathy, we'll call it a transversal, crossing through our parallel lines like this. One of the patterns that we get is what we call the Z pattern, and that tells us that when these lines are parallel to each other, the angles in the little corners of the Z here are equal. So angle A and angle B would be equal in this case, as long as those lines are parallel. So that's the Z pattern. The technical name for it is alternate angle. If we start with another pair of parallel lines, and we draw a transversal or a line through them again, then we can also make what's called the F pattern. The F pattern is when we have angles like that are both either underneath the line or just above the line. And they make the F pattern because you can see that F shape, that letter in the diagram. And again, these angles are equal. So if this is angle A and this is angle B, then angle A equals angle B. And the same for the angles on top of the line. Angle X equals angle F. So that makes it really easy to find out unknown angles. There's one more angle property with parallel lines, and that's the C pattern, but we don't use the C pattern very much. C pattern is the letter C, and if we have an angle here and call that A, and an angle here and call that B, then A plus B always adds up to 180 degrees. And we don't use that very much, but most of the time we can find a Z or an F. And if those angles are equal, then that's less math that we have to do than doing 180 minus an angle. So let's take a look at what we have here in our diagram and see if we can use these three patterns, these three letters, to figure out the unknown angles. They've only started us off with one angle, and that's 32 degrees. And so if I use the F pattern, I know that angle A is also 32 degrees. And that's because of the F pattern. So I'll just put an F in brackets to show how I know that's true. Now I can make a Z, can't I? I can go like this and make a Z with the X and the A. So that tells me that angle X is also 32 degrees. And that's because of the Z pattern. So now we've got two of our unknown angles, but we still have three angles left. And so we can also, we can use the C pattern now, and we can get some more of our angles. So for instance, here is the letter C, and remember the relationship is that those two angles are supplementary. They always add up to 180. And so if A is 32, then Y has to be 180 minus 32, so that they'll add up to 180. And so angle Y, you can see that it's obtuse. It's actually going to be 148 degrees. And we use the C pattern to find that. There's other ways we could find it also. All right, so we are narrowing down our angles that are unknown here. If I go like this, like this, like this, then I hope you can see that I've made sort of an inside-out Z pattern, and I know angle Y is 148, and so that tells me that angle B is also 148 because Z pattern angles are always equal. And then the last angle that we have to find is angle Z, And we can now find angle Z using the F pattern. I know there's different ways that we can do it, but that's one way that we can do it because both of those angles, B and Z, are on top of the line and they make a backwards F shape. And so angle Z is also 148 degrees, and that's because of the F pattern. So you can also see patterns here where all of these angles are going to be adding up to 180 degrees. So all of our obtuse angles are 180 minus the acute angle, and all of the acute angles turned out to be equal. And so that will also help you when you're finding unknown angles with parallel lines. And you notice that all we have here is 32s and 148s. And so all of our acute angles were 32, and all of our obtuse angles were 148. Okay, so here's a fun question. This one is a pentagon. A pentagon has 5 sides, and we call this a regular pentagon, again, if we want to get all mathy, because regular means that all 5 sides are the same length, and those little tick marks tell us that that's true. So we know that with a triangle, all triangles have 180 degrees if you add up the 3 angles in a triangle. If we move to a rectangle, add one more side, we add another 180 degrees. So now we have 360 degrees for the sum of all of the angles. So it should make sense that if we move up to a pentagonal shape or a 5-sided shape, we're going to add another 180 degrees. And so this shape has a total of 560 degrees. If all the sides are the same, all the angles are the same, just like with an isosceles triangle. So every single one of these angles, we can see that each one is obtuse, and each one of those is going to be 540 divided by 5. And so we end up with 108 degrees for every angle in this pentagon. And so angle A has to be 108 degrees. Now, angle B is exterior. If I know that the interior angle is 108 and these guys line up on a straight line, then we know that the total for them is 180. And so B has to be whatever is left from 180 when I take out the 108 that's on the inside. And so that's going to leave me with 72 degrees for angle B. So I'll write angle B equals 72 degrees. So here we are with a triangle, and again, this is a special triangle because it's isosceles, and we know it's isosceles because these straight lines, these little ticks tell us that those 2 lines are the same length. When that happens, the 2 base angles are also the same, and so we could label this angle as angle X also. And so really, even though we have 2 unknown angles, we can find both angles because we know that if we take 180 for the whole triangle, and we subtract 56 for the top angle, and then we divide whatever's left over by 2, in other words, we're going to divide it equally into 2 of the same angles, then we end up with 124 divided by 2, or 62 degrees for each of those angles. So angle X equals 62 degrees. Now angle Y is supplementary with angle X. That means that X plus Y, because they're on a straight line, add up to 180 degrees. And so if angle X is 62 degrees, then angle Y has to be 180 minus 62, and so angle Y is 118 degrees. This example is asking us to use a property of angles that we call opposite angle theorem, OAT for short. And if they start us off just with one angle, in this case the 43 degrees, then opposite angle theorem says that when we make an X with our lines, when they're intersecting like this, that the angle right across, or opposite from, the other angle, like 43 and B, have to be the same size. And so that makes that easy. We can say angle B equals 43 degrees. Also, we have straight lines here and here, so we know that a straight angle is 180 degrees. That means that angle A is going to be 180, subtract 43 that we already had. And so we have 137 degrees left over for angle A. And also, because angle A is opposite angle C, then we know that angle C is 137 degrees also. So we're using supplementary angle theorem and opposite angle theorem to find the unknown angles in this diagram. All right, so here we are with angles drawn inside a circle. And the really important thing about this diagram is to realize that that letter C stands for center of the circle. And so one of our points is going right through the center of our circle. The other of our vertices here is right on the circumference of the circle. When that happens, we have what we call arrowheads. The angle down here, 96 degrees, which we can see is just slightly over 90, is obtuse, is always double the size of the acute angle that touches the circumference of the circle. And so x is 96 degrees just divided by 2. That's the relationship when we have this arrowhead pattern. And so we end up with 48 degrees for angle x and 96 degrees down here that was given. In this last example, the last one we called arrowheads. This one we used to call bow ties because it kind of looks like a bow tie. Think of a bow tie pasta or macaroni. And so we have 2 triangles. And the funny thing about these triangles is that the vertices of 2 of the angles in each triangle are touching the circumference of the circle. And so when we do this, we end up with the angle x up here being equal to the angle over here, 53 degrees. So angle x is going to be equal to 53 degrees. And the angle y down here being equal to this angle down here, 42 degrees. Finding z now is easy because we have 53 degrees and 42 degrees in this triangle. That makes 95 degrees. And so angle z has to be 180 minus 95 degrees. And so angle z is 85 degrees. And so z equals 85 degrees.